In this example, we're given a particle with a displacement function. If we want to find the velocity and acceleration functions, what we do is just differentiate the displacement function. So go ahead, that becomes 12 minus 6t squared, and we don't do any more. Now velocity has units of centimeters per second. We go on to our acceleration function and we'll do the differentiation of the velocity function. This time it'll be minus 12. Remember the units, centimeters per second per second. And to find the initial conditions, that will occur when time is equal to 0. We'll have initial conditions. So the initial condition for the displacement will be when time is 0. We just insert 12, 0 into each one of these. 0 cubed minus 1. This is minus 1 centimeters. So how do we interpret this? We say that the particle is 1 centimeter to the left of the origin. Now we look at the conditions of velocity at time is equal to 0. We just substitute the time here for 0 and we'll get a value of 12 and it'll be centimeters per second. And we interpret this as saying the particle is moving to the right with a speed of 12 centimeters per second. Okay, take note that if our displacement is a negative sign, like minus 1, the particle is going to be going to the left. And if our speed of our particle is positive, as in here, 12 centimeters per second, then the particle is going to move to the right. Okay, it's really important. So now we can have a look at the next step, which is the acceleration. So the acceleration will be minus 12, and we substitute for 0. We will just get 0 centimeters per second, which means that there is no acceleration. Now that's going to change the whole story, because if there is 0 acceleration, we can now say that the particle is moving to the right with a constant speed of 12 centimeters per second. In these questions, the velocity and the accelerations is really very much related. So you really need to look at both. So these are our initial conditions. What happens next is we need to find the change in velocity's direction. And these changes can be found by looking at the velocity function. So now I want to have a look at what happens when at C, find the times and positions when the particle reverses direction. Okay, our velocity function shows us 12 minus 6t squared. We will know when that direction is changed when the velocity is equal to 0. So we just equate this with 0 and say that 12 minus 6t. A little bit of algebra needs to be done around here. So let's just take out the 6 out and we're left with 2 minus t squared. Now using the difference of two squares, we can continue difference of two squares. We can now factorize this. So it becomes root 2 minus t and root 2 plus t. And this will give you the values of time when the particle changes direction, which will be at time is root 2 and also at time minus root 2. Now you can see that this particular value is not appropriate because time cannot be negative. Only at t equals root 2 do we have a change of direction for velocity. So we now know that that particle will reverse its position at that time. Reverse its position. But where is this position? This is the other question that you're asked there. To look at where that position is, we need to now go back into our displacement function and have a look at it at that particular time. So what we're going to do is substitute root 2 into our displacement function, and that's going to be 12 root 2 minus 2 root 2, which has been all to the power of 3 minus 1. Okay, that looks really a little bit complicated, but we will simplify it. So we know that that's 12 root 2. Can we now simplify root 2 to the power of 3? Okay, I'll just do this to the side over here. Root 2 to the power of 3 basically means that you're multiplying root 2 3 times. And as you know that if you multiply root 2 and root 2, you will just get 2 root 2. So we now know that we've got 2 root 2. So I'm going to insert that times 2 root 2 and minus 1. I can now go further and say that 2 times 2 is 4 root 2 minus 1, and because 12 root 2 take 4 root 2 is equal to 8 root 2 minus 1. Once again, I'm saying all this because I am explaining in detail. You do not need to show all this, you can go straight to the end. And if you work it out on your calculator, that becomes to approximately 10.3. That will be centimeters. So it will give you an idea where it actually stands on the sign diagram. So the particle changes its direction at 10.3 centimeters to the right of the origin at t root 2 seconds. To work out number D, at what time is the particle's speed increasing, we need to look at two functions. Both of them I've said before, one is the velocity and one is the acceleration, because the velocity and acceleration are related to each other, to its speed. To examine the speed, whether it is increasing or decreasing, I need to examine the sign diagrams of both the velocity and the acceleration. By drawing the sign test of the velocity, first, velocity, we know that its time needs to start at 0, so I can draw a wall here. And we also found out that this happens at root 2. That is when the time is root 2. We need to find out what happens before root 2 and after. By substituting root 2 into a velocity function, we can see that that's going to be actually positive, and that part of it is going to be negative. Now, we also need to draw another sign diagram, and this time of the acceleration function time. Once again, it starts with this. Now, we know that the acceleration, just from the function over here, is going to be negative. And the definition of a particle that its speed is increasing says that its sign diagrams must be both positive or both negative. Where does this happen? It only happens in both are negative when the velocity is negative and when the acceleration is negative. Well, this means that the particle speed is increasing at time greater than √2. So what's the difference with the question when you're asked when is the velocity increasing for number 2? I'll just draw a line here so that we don't get this mixed up. Now, so far I've answered D here, the speed increasing. Well, what about the velocity increasing? Well, acceleration is the main factor that makes the velocity increase. So for velocity to increase, the acceleration must also increase. So if AT and positive, then velocity increases. Clearly, we do not have this situation in our case because the acceleration is negative. This brings to a very important conclusion. If VT and AT are both positive or negative, then speed will increase. But velocity increases only when AT positive. Okay, so the motion diagram now can be drawn from this, all of this information. We've got the position here. Let's start with the origin over here, -1, -2. And from what I remember, we need to go 1, 2, 3, 4, 5, 6, 7, 8, 9, at least 10, because the particle changes direction at 10 centimeters. So that's about 10 over here. The particle starts at -1, okay, and it changes direction somewhere at 10.3. So we can just draw that as the particle moves to there, and it now reverses back. And this happens at time is equal to √2 seconds. And this is our sign diagram.